All right, welcome back, Algebra 1. Today we are looking at solving quadratics. You had a little bit of an interactivity on Desmos of this, where you were looking at different quadratics, you were trying to find their factors, and then you were trying to find their x-intercepts, or the solutions to those quadratics using those factors. So we had a little bit of an intro to this. But looking at this problem here, we're trying to figure out what are the intersections of the dotted lines represent for each of these graphs. And if we look at the intersections are where those two lines cross or intersect. So we have a point here at -5, 0, and -1, 0 on my first graph. If I look at this one, I have a point here at -5, 4, and a point at -1, 4. And then lastly, I have a point at -5, 8, and -1, 8. 8. There we go. So if we look at the intersection for each of these different graphs, I guess I use the same colors on two of them. If we look at the intersections for each of these different graphs, they show us the solution to these different problems. On the first one, we're looking for when does this quadratic equal 0? When does this quadratic equal 4? When does this quadratic equal 8? So it's asking us when does the quadratic equal a certain value. So if you want to figure out when does a quadratic equal 29, we would have that equation of that quadratic, whatever the equation of that quadratic is, equals 29, and then you just have to solve for that intersection. Now we can do this on Desmos. That's pretty easy. If you graph 0 equals x squared plus 6x plus 5, it should show you where that quadratic equals. Or you might have to do x squared plus 6x plus 5 in one line, and then x or y equals 0 in another line. And you should be able to see when they cross. Or same with 4, same with 8 for those other different quadratics. Now, one thing we looked at on in your little intro is that one way we can also solve this, besides just graphing and seeing when does that quadratic equal it, by just graphing a line at equals 5, so like y equals 5, and y equals x squared minus 8x plus 20, rather than graphing those and seeing where those 2 points are, one thing we can do is we can change the problem a little bit. We can change this because we already know, we've already talked about before how to solve for when a quadratic equals 0. We know how to solve for like the x-intercepts, or like solve essentially when a quadratic equals 0. We know how to solve for those. So one thing we can do is we can change the problem. If you have a quadratic like 5 equals x squared minus 8x plus 20, we can inverse the 5. We can work so that all of one side of that quadratic is going to equal 0. So I saw that this side had a 5, or I had a 5, so I want to inverse my 5 so that it's equal to 0. But if I inverse my 5 on one side of my equation, I have to inverse my 5 on the other. So we kind of have to think, okay, where does that 5 need to go? Well, the 5 is a constant number. It doesn't have an x. So the only like term that it's going to have is that 20. So 20 minus 5 is going to be 15. And now I have 0 equals x squared minus 8x plus 15. And we know how to solve this. I can either graph it on Desmos and find my solutions that way, find my solutions at 3, 0, and 5, 0. So I know my answers would be 3 and 5. Or I could factor this. I could factor this and get, we should get x minus 3 as one factor and x minus 5 as another factor. If we were to factor them, obviously you'd have to do your box and diamond method. You wouldn't just know those off the top of your head. But then you would be able to see x equals 3 is one solution and x equals 5 is your other solution, because we know it's always going to be opposite. We can always set it up as x minus 3 equals 0, add 3, and we get x equals 3. Or x minus 5 equals 0, add 5, and we get x equals 5. We know that works because that is our zero product property. When you're looking for when two factors equal 0, The only time two multiplied numbers equal 0 is if one of those numbers are 0. So that means x minus 3 has to be 0, or x minus 5 would have to be 0. Well, when does x minus 3 equal 0? Well, x minus 3 only equals 0 if x is 3. When does x minus 5 equal 0? Well, x minus 5 only equals 0 when x is 5. So those would be our two solutions of when this quadratic would potentially equal 0. But we know this isn't the original quadratic. The original quadratic was x squared minus 5x plus 20, and we're looking when it equals 5, but we can solve for it by changing one side to make it equal 0. So we can manipulate these questions like that. So let's look at an example of these. So what are the zeros for the equation 2x squared plus 11x equals 21? So what is the solution to this problem? Well, if I have 2x squared plus 11x equals 21, all I need to do is inverse this so one of my sides is equal to 0, and then I can solve that quadratic just normally using my factoring. So I'm going to inverse 21, and this is going to cancel out, so that's going to be equal to 0. Now, the thing is, I have to think, what is 21 alike terms with? Is it alike terms with x squared? Is it alike terms with 11x? Well, actually, no, it's not alike terms with either of those, because one has an x squared, one has an x. Neither of those are like terms with 21, which is a constant. So I'm just going to leave this as 2x squared plus 11x, and I'm just going to put minus 21 in that c spot in our ax plus bx, or ax squared plus bx plus c, that standard form equation. I'm just going to put that minus 21 at that last spot because there's no other numbers there. And now that I have 2x squared plus 11x minus 21, I can easily factor this. I can create my box and my diamond, or my box and my x, and I could solve. So in my numerator, I put my negative 21 times 2x, which is going to give me negative 42x. My bottom of my x, I'm going to put my 11x, my middle term. And I have to think, okay, what are two numbers that multiply to get negative 42, add to get 11? These ones are a little bit harder to come off with the top of your head, but we can come up with 14x and negative 3x multiply to get negative 42x squared, and then add to get 11. So I know 14x and negative 3x are going to be my two factors. From there, I can start filling in my box. I have a 2x squared and a negative 21 that's going to fill my first and my last. 14x and 11x are going to fill in the other two spots. So I'll put 14x and 11x. So now I just need to fill in the outside to get my two factors. Well, what are some numbers that are on the outside? What are two numbers that multiply to create 2x squared? Well, I know it has to have an x and an x in each of them. I know a 2 has to go into one of those locations because it's a 2x squared. So a 2 and a 1 are going to multiply to create 2. So one of these is going to be a 1, one of these is going to be 2. Well, if I think about it, this row has even numbers. This row does not have 11. Is not divisible by 2. So I know 2 needs to go in my numerator because 14 is divisible by 2. So this is just going to stay 1x. Well, 1x times what becomes 11x? Well, 1x times 11, so that's going to be a plus 11. 2x times what becomes 14x? Well, 2x times 7. What did I? Oh, I'm sorry. I put 11x, not negative 3x. I apologize. I'm sorry. Let me fix that. This is negative 3x. So 1x times what becomes negative 3x? Well, 1x times negative 3. And then 2x times what becomes 14x? 2x times 7. So my two factors that I get are 2x minus 3 and x, 1x or x plus 7. And these are going to be my two factors that are going to equal 0. Well, I know based off the zero product property, in order to solve for 0, I just have to set each of these factors equal to 0, and then I will be done. So I'll have 2x minus 3 equals 0, and x plus 7 equals 0. And then all I have to do is solve these two-step equations, and I'm good. So this one's easy to do first. Just subtract 7, and x equals negative 7 is one of our solutions. This one's a little bit harder. I have to do two steps. I add 3 to add 3, so that gives us 2x equals 3. Divide by 2, and we get x equaling 1.5. So those are our two factors, two solutions of our quadratic. The 2 times this equation equals 21 is going to be at x equals 1.5 and at x equals negative 7. Those are the two locations at which 2x squared plus 1x or plus 11x equals 21. Now moving on from here, what are the solutions to the quadratic equation x squared minus 5x equals negative 3? Well, once again, I know I can solve this. I can come up with a good solution to this problem. Oh, I dropped my paper, so maybe I can't. If I take my quadratic, I I know I start with x squared minus 5x equals negative 3. I know all I need to do is first inverse that one side. So I'm going to add 3 to inverse my constant. Once again, I need to add 3 to this side then. So x squared minus 5x plus 3 equals 0. I know it's going to be plus 3 because once again, there was not a constant on that side. I had an x squared and a negative 5x. So neither of those numbers are going to add to 3 because none of them were like terms. But from here, now I can factor. So I create my box, create my diamond. So in my numerator, I'm having 3x squared. In my denominator, I'm having negative 5x. Well, I need to think, what are some numbers that multiply to get negative 3? Or sorry, positive 3. What are some numbers that multiply to get positive 3? Well, the only two numbers that multiply to get positive 3 is going to be 1 times 3. Well, or 1 times 3 or negative 1 times negative 3, I guess also gives us positive 3. Well, do either of these add together to give me negative 5? Well, 1 plus 3 is 4. Negative 1 plus negative 3 is negative 4. So neither of those actually are going to work to get negative 5. So this is an example of an unfactorable problem. So sometimes we're going to run into unfactorable equations, unfactorable problems, and we cannot solve this using our factoring method. Luckily, we do know of another way in order to solve for x-intercepts. This is not our only method in order to solve for zeros or solutions or in order to solve for x-intercepts. So one thing we can do is we can also just graph this problem normally on Desmos, and we can find our x-intercepts that way. So my problem was, if I pull up Desmos, it was x squared minus 5x plus 3. And if we look at, so this is our equation. If we look to see when this quadratic equals 0, we equal 0 at those two x-intercepts. So we have one x-intercept of 0.697 and the other x-intercept at 4.303. So we have two x-intercepts. One is x equals 0.697 and the other is x equals 4.303. Now, I don't know about you, but I would not have came up with those factors as two numbers that multiply to give me 3 add to give me negative 5, or the inverses of these, in fact. So these are not going to be easy numbers to come up with. So sometimes it is possible for us to not come up with factorable solutions. So when that occurs, we're going to run into situations like these, where the easiest thing to do is just graph it on Desmos, look for those x-intercepts, and then go on from there and say, okay, it's not factorable. Here are my two solutions that I came up with. The last thing I want to talk about really quick is sometimes when we solve these problems, we have three types of solutions. So when we graph a quadratic, we are going to get three potential solutions. So I know quadratics always have that U shape. So if I'm looking for when a quadratic is equal to 0, I know there's three potential ways that my quadratic could be equal to 0. My quadratic could look something like this, and it could be equal to 0 twice because it's touching the graph twice. And that doesn't matter whether it's up or down. It could touch the graph, could touch the x-axis twice. My quadratic could be looking like this and touch the x-axis at only one location. And so this gives me two solutions. This gives me one solution. And then it's also possible for a quadratic to look like this, where there is no spot where a quadratic hits that x-axis. So this would be solutions. So when we solve these quadratic equations, when we solve these quadratic functions and we're looking for when x equals something, or when the quadratic is equal to a certain value, we're going to get three potential options. We're going to get two solutions, we're going to get one solution, and we're going to get no solutions. Now, most of the time, you're going to get two solutions. Sometimes you might get one solution. And then every now and then, we might run into quadratics that have no solutions. It's possible for that quadratic to just never touch that x-axis, so it's possible for it to never have a solution. If that's okay, that's okay. We run into that in certain situations. It happens. We'll talk about what we can do with that in the future in a bit. But these are the three ways that we will get solutions for quadratics. Two solutions, one solution, or no solutions. Now, once again, the easiest method to probably do is try to factor it, set each of those factors equal to 0, and then you have your two solutions from there. If you can't factor it, if you can't come up with values, plug it into Desmos, see if it has factors. So it's possible that you might get two factors that were just really crazy numbers like 0.679 and 4.343 or whatever, and you do have some solutions. It's possible that you might get no solutions when you plug it into Desmos. It's possible that you just might figure out that the graph never touches the x-axis, and that's okay. So those are two ways for us to check our answers, is using that Desmos when we do run into those unfactorable problems. That is where we'll end it for today. Let me know if you have any questions. You have some practice and spiraling over this and an exit slip. Have a great rest of your day.